Hello, everybody, and welcome to this third part of the Deep Learning Crash Course. And today we are going to be discussing majorly about medical imaging and medical image segmentation. The topics that would be covered is the first one would be thinking outside the RGB spectrum, then would be followed by just some introduction to the basic modalities that are used in medical imaging. Then we will be following it up with classification to segmentation and why suddenly everything is just so weird and different. Then we would be talking about why the metrics change in medical imaging and we focus more on the true positives and the false positives. Then we would be talking about how to understand the data better in medical imaging, and then finally we would be talking about a very crucial topic is that if I keep changing my medical imaging modalities every time, would I have to study them? Now that's a question to ponder upon. Now, starting with thinking outside the RGB spectrum. So as you can see in the image in the top right corner over here, all the pixels are between 0 to 255 in a 3-channel mode. So this is what we call an RGB image. But in medical imaging, we aren't so lucky. So the next question becomes, what if they are not, like what if it's a black and white image like MNIST? Then things change. As you guys can see in the very popular modalities over here as MRI, CT and sonogram, all of these images are black and white. And not just black and white, but they vary in intensity. So these images aren't limited to 0 to 255, but they can go as high as 0 to 65, 536. That's like a int 64 if I'm correct. So that's why we have to treat medical images quite differently. Now, some very general introduction to modalities. One of the popular ones that we see is MRI, and I'm just taking an example of brain because that's a project that I've worked on previously. And as you guys can see, this is the histogram of all the intensities that lie between the MRI images. So obviously this is just capped at 4,000 right now, but they can go as high as 12,000, 13,000 as I remember. Obviously that's just some noise, but still. So as you guys can see, we have different intensities, and these come to different parts of the brain. So for example, CSF, what CSF means is the cerebrospinal fluid that can be seen around all these regions. Now, the other intensities such as fat, skin and other are at a different rate. So as we see from over here, every single intensity is a feature in itself. So these features cannot be lost quite simply as they get lost in normal imaging. So here you are seeing these 4 popular modalities that are available in MRI. So MRI submodalities that are available in MRI, which are T1 with post contrast, T2 flare and T2 weighted. And this is a segmentation of the tumor that we want to generate in the future. Now, again, moving forward to another very particular modality is CT. One of the most best things about CT is that it is defined in Hounsfield unit, and at every single intensity, there is you can recognize a particular tissue from it. So for example, we see over here, we have the CT of a kidney region, and as you guys can see over here, kidneys can be checked out pretty easily. These are again similar challenges that we faced in CT modality. And what we mean by this is, as you can see in this very nicely annotated figure, that every single modality and every single intensity that you look at over here is defining to a particular region. So that's why CT imaging is quite crucial when you are learning about medical imaging. Now, moving forward, what happens between classification and segmentation and why everything becomes different all of a sudden? As you guys can see in this very nice example over here, let's say you deploy an app which is used by clinicians every day. Let's just take a very random example of this one, that saying you're pregnant to a woman makes sense, and that's why it's called a true positive. saying you're not pregnant to a man also makes sense, and that's why it's called true negative. Now, it would be weird if you're telling a man he's pregnant, wouldn't it? So, it's called a false positive. And again, these are punishable because, as you guys can see in the examples coming forward, that this could be pretty dangerous. And similarly, telling a pregnant woman she's not pregnant is also kind of risky. As we have shown a classification example over here, we are showing an example of a normal brain with some benign tumor, and a brain with malignant tumor. And similarly, a chest X-ray with which is normal, again bacterial pneumonia and viral pneumonia. Again, these have different medications, so your app kind of becomes very important. So that's why your false positives and false negatives could be really costly to someone's life. So, talking about why true positives and false positives are more important in medical imaging. Now, as you guys can see in this example, we have a normal brain, and we have a low-grade glioma, and we have a high-grade glioma. Now, low-grade gliomas could be meningiomas and astrocytomas, whereas high-grade gliomas could be glioblastoma multiforme. Now, let's talk about classification of these. So, for example, a normal brain is classified as a normal brain, no treatment is done. But if a normal brain is classified as a low grade, that person will receive radiation therapy and that person will die soon. Similarly, a normal brain for a high grade, there would be an attempt to resect, that means to open up your skull and remove the tumor, which could be bad if they don't find any tumor. That's why the yellow. Red means you're dying. So, moving forward, let's say we have a low grade glioma, which is classified as normal. So you're telling a person that he has a tumor that he doesn't, which means he's going to die soon. Now, the correct response is giving the person radiation therapy and possibly resection. And similarly, there could be another resection plus therapy attempt, as a low grade glioma is classified as a high grade glioma. Again, I'm not a clinical folk, so I'm not the best person to know these kinds of stuff, but I'm just giving an example. Similarly, there is a high grade glioma. Now, if you classify it as normal, that person will die soon because you're not treating him. Why would you do that to him? So exactly, don't miss it. Similarly, if it's classified as a low grade glioma, maybe the tumor doesn't respond to therapy and the person dies soon anyway. So one of the best option always is resection plus therapy, and that's the thing that should be done. So as you guys can see, if you miss a choice, the person could suffer fatal consequences, and that's like 3 out of, you have to be correct all the time. That's the problem with medical imaging. You have to be as correct as you can. Now, moving forward, understanding data better. So for example, these images, as you guys can see, the images could be 2D, 3D, or 4D. This is a 4D MRI, by the way. It's just not showing correctly, but these are time points. And the thing is, this is such a diverse data type that normal neural networks, the plans that we use for normal neural network training, just doesn't work. So that's our problem, and that's the goal that we try to solve. The big question arrives, do you have to study every single time, every single modality? Sadly, the answer is yes. Every single time you work with a new modality, you need to have a base idea about what the modality does and what the intensities are and what our regions of interest are. And although you don't have to study as much as the physicians or the technicians do, you have to study just enough that you can solve the problem. And that's the goal. So this is usually solved with just giving out a read through the literature work and checking how previously the attempts have been made to solve these problems. So that's about it, guys. Again, if you like this content, please make sure to give it a like and share the video to the people who can be helped by this, and subscribe if you haven't already, and let me know in the comment section below if there are a few more topics that you would like me to cover. Also, if you really like my content, please feel free to support me on Patreon, and until then, stay awesome.